Okay, so why don't we write another interesting function? I'm going to call this function uh, apply all. So this is kind of cool. The way this function works is it's a really useful mathematical mapping function. So we actually had an instance. I was talking with the sophomores about this because there's a way when in JavaScript when you receive a list, you can map a particular function, JavaScript function, to all the items in that list. And so we can do something very similar here. So we're going to call this apply all function. And so here's how we'd like it to work. If I say apply all. If I say apply all, then, and I pass in a function, like let's say, I don't know, cube, all right? I'm gonna have to define cube in a second, but let's say I do apply all cube. So cube's gonna cube my numbers for me. And then I pass in a list, 1, 2, 3. What I should get back as a result is the list 1 cubed, 2 cubed, and 3 cubed. That's the idea of apply all right? So one thing I want to note here, which is kind of interesting, is this thing cube, the argument, this first argument to apply all is the name of a function. So you can pass in the name of a function and have that function get executed against all of the elements of the list, as long as the elements in the list contain the right number of arguments for the function. In this case, cube takes 1 argument. So we pass in the first element in the list to cube, then we pass in the second to a second call to cube, and the third to a third call to cube. All right, it turns out the code to make this work is actually pretty straightforward. So let's write that code. So define apply all. So the first argument to apply all is a function, and the second argument is a list. Now, we're just basically stripping the elements from the list and running the apply all function on each element in the list. So we can do a cond, and our base case is going to be when we're done processing the list. So if the list is empty, then we're done. And we'll return the empty list. Otherwise, what we're going to do is construct a list by taking the first item out of the list and with the function applied to it. All right. So if we're doing apply all cube 1, 2, 3, we're going to take the 1 out of the list. All right, and apply cube to it. So that would be function of the first element of the list. In this case, that'll return 1. And then that value that gets returned is going to be appended to another call, recursive call, to apply all with the function and the rest of the list. Cool. So let's compile that, make sure it all looks good. Whoops. Let's see. Empty list. Let's try that. Perfect. Okay. So now I haven't written the cube function. Let's try apply all on something we already know. So apply all to, how about reverse? Reverse. And we're going to pass in a list. And the list contains A, B, C, D, E, F, G, H, I. Okay. So we're passing reverse. We're calling apply all with reverse, our reverse function, and we're going to have it work on 3 separate lists: the ABC list, the DEF list, and the GHI list. So effectively reverse will be applied to each of the items in this initial list. So ABC, then DEF, then GHI, right? And now we see we've got the result returned is a series of lists with the list elements reversed in each one of them. So it'd be cool to apply all to cube. Let's write a cube function. That's pretty straightforward. Define cube, which takes in x, and it's going to return x cubed. All right, let's compile that. And now if we can just test it first. Cube 3 should be 27. All right, now let's try apply all. One, two, three. Okay, so we get lists with 1, 8, and 27. Now, something that's kind of interesting about this. It's kind of a pain to write that cube function just to have it written up here and stored. There's situations where you have a function that it's fairly simple and you just like to, it's sort of like a one-off function. You like to use it in some of your other code. So rather than defining cube, which is a pretty trivial function, we can define something called a nameless function. These are called lambda functions. So the way you define a nameless function is you actually define the function in line with where you're using it. All right. So I can do a nameless function here, and instead of saying cube, calling cube, I can create a nameless function which does the cube. So I'm going to say lambda x and define what this nameless function does. And now pass in 1, 2, 3. So what did I just do here? I said I would like apply all, which expects a function, to use this function that I've just defined in line. The function doesn't have a name. It's called the lambda function. So I guess technically it has a name, but this is a name you can reuse over and over again. So here I'm saying the lambda function is going to cube numbers. I'll run that. But I can just do it all over again, and I'll have the lambda function square the numbers instead. So I can just reuse it. And that way I don't have to go up here and define little one-off functions when I don't really need them. All right, cool. Well, that takes care of apply all and lambda. Those are very useful when you're doing functional programming. So I wanted to talk now about how to do output. So there may be situations where you're interested in getting some output to the user without it being the return value of the function. Those times when you want to do that are extremely rare. So I actually would highly recommend, even though I'm showing you how to do this, I would highly recommend that you avoid it unless you're doing some special super cool debugging, which I'll show you how to do in a second. So I'm going to show you how to do this, but I'm saying in general, things will go much smoother for you if you just think about calling functions, having those functions return values, and just looking at the result of those values. If you introduce anything else that's procedural in your code, you're violating the principles of functional programming, and that can make for problems when you're coding. When you're programming functionally, there's this really nice interconnectedness of things calling things, which produce results that you're expecting. When you add other stuff to it, like what I'm about to show you, that can create problems. So I can write a method called display. Now, what just happened when I said display single quote A? Well, it displayed A. That looks very much like a string that I would be used to working with, and so that feels kind of good, and that's different from this. Well, first of all, or this, all right? And in fact, the value of this display A is different. The value of this quote A, single quote A, that is the atom A. What happens when you say display A is you get something called a functional side effect. Display is the function, and its job is to print out a string to the screen. That's what this A is. It's a string. It is not, or it's just screen text. It is not a value. The value from display A is different. It's actually, well, I'll tell you what it is. It's the value from display A is void. So display A, that function, returns a void. Now it looks like it's returning this A, but that's not what's actually happening. Display A is printing the string A to the screen. That's what it does. Then it returns void. So for example, if I were to try to use this if I were to try to use that A from display A in a list, to build up a list, this is what I get. List void with the A printed out in front. Well, what's going on here? Well, display A says print out the atom A, so it prints out A. That is not the return value of the function. Everything in this language returns a value. That's how the language works. And so the return value of display A is void. That void, via cons, gets inserted in this empty list. And so we end up with that strange value. All right. Given how weird this is, how could you actually use display A? Well, you can use it in a very interesting way to do some debugging. So what I'm about to show you is not something that I recommend. I recommend and generally try to use the debugger, but if you're going crazy and you need to figure out what the values of certain arguments are in a function that you're trying to debug, you can use something like this, right? So we're going to use it with a special function called the let function. So I'm going to define a Pythagoras function that takes two arguments in, A and B. And so it's going to give me, it's going to compute C from the sides A and B, right? C squared equals A squared plus B squared, and then C equals the square root of A squared plus B squared. So that's what we're going to compute. But I'm going to use this special let function to show me interim values getting calculated and print out those interim values. All right, so I'm going to say A squared, I'll say A2, that stands for A squared. And I'm going to define A squared as star A. So I just defined a variable. A little weird. It's actually called a name, it's called a name binding. So A2 is bound to this result, or bound to this function. So I'm sort of defining this function, defining a local function A2, that's a way of thinking about it, to this, all right? And I'm going to define another one, B squared as star B. Now, here's where things get a little weird. I can actually print out the values of A squared and B squared by using display. So here's how I'm going to do it. I'm going to create some variables. D0 is equal to display of, and I'm going to put in a string here. So the string is going to be A squared equals and D1 is going to be equal to display of A2, and D3 is going to be equal to, bound to, I'm saying equal to, it's not really, it's just bound to display A4, display B2, B squared. Oh, sorry, I need to do another regular display. So display b squared equals, and d4 display b squared. All right, and now I happen to know that display puts everything on the same line. So if I want to display a new line, I think I want to do that here, D2, display new line. And I'm going to do the same thing here, D5, display new line. Okay, so let me explain what happens here. So this A2 is going to get bound to the star AA, B2 is going to get bound to star BB, D0 through D5 are going to get bound to the result of these display expressions getting evaluated. And these are going to trigger things to get printed out at the screen, including the value of A2 and the value of B2, plus some \n's, which are new lines. Now, once you've defined your name bindings using the let, what you can do is you can use them in expressions. So I'm going to do that. I'm going to say, give me the square root of a squared plus b squared. And that is what this function is going to return. Okay, and let's compile it. Let's see what happened here. It's saying A2 isn't defined. Now, why is that? I think I just defined it right here. A2, this variable is not defined, but I got my let statement here. Let's see if I've got anything else going on here that might explain that. It's clearly defined right there. That's good. There's my square root. Let me just take that out for a moment and see what happens. Take that out as well for a second. And I'll say Pythagoras 1, 2. Okay, that's cool. But for some reason it doesn't like my, it does not like my A2 and B2. And the reason for that is, I'm just looking at my notes now to see what I might have messed up here. Oh, I don't think I can, I'm not sure I can do that. I can print out A and B, but I can't print out A2 and B2, those name bindings. So, because they haven't been used yet. Um, what I can do is I can display star AA, and I can display star BB, and let's try that. Oops. Okay, cool. So A squared is 1, B squared is 2, and we've got some lovely values here. So that's something that you can do with display to get you some debugging information in code that you're working on. You can use these let statements. So one technique is you could use the let statements, for example, to print out the value of an expression that you want to evaluate, or I could have printed out the value of A and B as well. That's totally fine. So let's do that. Let's change this. Yeah, we can, I'll leave those in here, but we'll just display the value of A. And we'll display the value of B. All right. And there's the value of A and B. So I can get some information. And you can imagine with recursive calls, this could be really useful. All right, that takes care of let and display. Generally speaking, I think it's better to use the debugger to trace down things because you can see pretty easily in the debugger the value of parameters that are being passed in, and display is really violating the whole idea of functional programming. It's doing something, you're seeing the result on the screen, that result is not a value or anything like that, and then it returns void. So it's really hard to use this outside of let statements, which are, I don't know, I'm not really a big fan of let statements. All right.